let's do a little engineering here. So this is a formula that will give us the capacitance of a capacitor, okay? This is a constant that we use just so that we can get farads for that. This is the area of the plates. This is the plate separation. And so this makes sense, right? The bigger the area, the more charge we can get on there, right? And then the closer we get those plates together, the less work it is to get the charge on those plates. And that's because, of course, the positives and the negatives will attract each other. So we have to do less work to charge the capacitor. And the less work we do, the less voltage there is across it. And remember that C is what? Q over V, right? So the closer these plates are together, the easier it is to get these positives and negatives on there because they're so close to each other. If they're separated by a large distance, it's more work. That's an intuitive way to sort of think about this, right? And then the other thing that's kind of cool is that we can put, notice that this permittivity of the dielectric, right? If it's just air, right, or a vacuum, the air and a vacuum are very similar, right? We use 8.85 times 10 to the minus 12th coulombs squared, newtons to the minus 1, meters to the minus 2. We use that. This is the permittivity of free space or of a vacuum. If it's some other dielectric, we would use these multipliers. And basically any capacitor you buy, if it's not a variable capacitor with those plates like we looked at, it's got something in between it besides air. Like, for example, if you use strontium titanate, your capacitor will be 3 times as strong as it is if you use air. That's the way this works. And the reason that a dielectric works that way is that remember that if we can reduce the voltage, we increase the capacitance. Remember ultimately that that voltage is of the electric field times the distance separating it, right? And if we can reduce that electric field, we can increase the capacitance. And here's how it works, right? These dielectrics are polar molecules, and so the capacitor is generating an electric field this way, right? This is the positive side down here. Here's the negative side. It goes from positive to negative. Notice that the dielectric creates an electric field inside of it that cancels that field out. So the electric field gets to be less, right? The molecules, the charge doesn't move because they're insulators. The molecules just rotate, so the positive side is toward the negative plate and the negative side is toward the positive plate. Every molecule generates an electric field. That electric field, the aggregate electric field, sort of cancels out that external field, reducing this electric field, increasing the capacitance. That's sort of a short version of the electrical engineer. When you go and study electrical engineering, you can come back and straighten me out on this. Okay. Let's do an example problem here. Oh, no example problem for us. Okay. This is sort of a diagram of how they make these CAN capacitors like that. They roll up an insulator like that. And electrolytic ones, I believe, use a layer of oxide that's quite thin, right? And so the distance is very small. I think it's like on the order of microns thick. Let's do no example problem for me. This is a variable capacitor. So what they're doing here is they're changing the area, right? So C is area over, I'm like, right? So what they're doing is just changing the area of overlap there. They can make it bigger or smaller by rotating that knob. Okay, I do believe if I hit the right arrow, we're going to see the example problem. So, okay, so it's an air gap capacitor. So we're going to use this as this. This is going to go in for that. We're going to turn this centimeters into meters by putting the decimal point there. Right, and I think we're good, right? Our area, our C is equal to 8.85 times 10 to the minus 12th times, let's see, what's our area is 0.216 times 0.279. And then it's 3 millimeters, so I'm going to go 3 times 10 to the minus 3rd. I'm just using this formula. Okay, so here we go. If I do that, I get 1.7777. This is an awesome number. Then it's 88. I want to know, does it do like 9999 or something like that? Times 10 to the minus 10th. And this is farads. That's a 10. This would be, of course, 117.8 times 10 to the minus 11th farads. It's 178 times 10 to the minus 12th farads. or 178 picofarads. So that'll just give you an idea, right? This is two 8.5 by 11 sheets of paper, 3 millimeters apart, so you can visualize what this capacitor is. It doesn't have anything special between it. It's 178 picofarads. By the way, they can get that much capacitance in a much smaller package by using a better dielectric than air. Just going to say.